I went to this internet. We're taping. Did it go 3, 2, 1? Of course it didn't. All right. So we were gonna go through this whole page and have the students fill out their chart and then check. Here's the point. Do this in like 5 minutes, and then I'll just shove the answers at you and then continue with the notes. What am I getting my phone out for? A timer, just to time myself. I'm gonna go to 4 minutes. 4 minutes of talking about this page. Okay, so the difference between angular displacements and linear displacement. I got a stamp too, so this was and I'm not going to stamp your Friday's homework because I don't have time. But it's this. Okay, so what happens in 10 seconds? You agree that this goes from here to here, right? In 10 seconds, it goes to the two hand. You ever seen a clock like this before? I hope, right? Yes. Okay. New girl, we go like this when teachers like, okay. Sorry, she's gonna hate this. All right, but anyway, what fraction of a rotation did we do there then? What fraction of a rotation? It's pretty easy. I think I screwed up the other hour. No one stopped me. I think all these fractions are wrong. So I just did 2 what? 2 what's of a rotation? 12. So let's show how the notes are all wrong in the other hour. All right. So that's well, I guess it's I guess I could say this. So 2/12, which is still 1. What is happening here? So I guess this does work out. I did 10 seconds out of 60. Yeah, so I guess that's fine. And then what's a full rotation? What's a full rotation from Friday? How many radians? 2 pi. So I do 10 or 1/6 of a rotation in a minute, right? So it doesn't say anything about what do I want my angular speed in, minutes or seconds. So let's just do it in minutes without that. Okay, and then what we were supposed to ask next is what's the distance covered by the tip of the hand? Well, that's different. The tip of the hand goes from here to here, so that is actually a concrete distance. That's arc length, right? But traveled over a unit of time, which we do have established as per minute. So what is that arc length? Well, it's 2 pi r, but then it's 1/6 of that, right? Don't you agree? Okay, because it's 1/6 of a rotation. 2 pi r represents the whole circumference. And then what did it say the radius is? What is the radius? Can you read the question, please, and tell me what the radius is so I don't have to scroll up? Huh? 30 centimeters. Okay, 30 centimeters. All right, and then I have a version of that, but I actually stuck 30 just in front of that angular velocity. That's what you're going to find out. This is an alternative form of this kind of question. So I don't know. I'm going to, with our shortened time here, this is really ultimately what we wanted to do. And I added this last row because what happens in 60 seconds, wouldn't you agree that it does a 2 pi radian? All right. And then what would the tip hand do? The tip hand would do 1 full circumference all the way around and travel all of that distance, which is a full 2 pi times r. So that's why at the end, I just multiply the previous answer by 30 to get the second column. That's what we discovered or threw in there. So it'd be 30 times 2 pi, which is 60 pi. So you do 60 pi centimeters per minute is what happens. I'll talk about this conversion. 100 radians turn into centimeters. It's all different versions of this formula. And then all these previous ones, 25 seconds, 30 seconds, 50 seconds. That's the fractional angular or linear distance you travel, because that's what it means as far as those seconds are concerned. Okay, so now what's the angular velocity in of the second hand in seconds? You do 2 pi radians. Okay, and I did want to move on from this. We're going to get to it. And actually, the next stuff that I do, we'll come back to this and make sense out of it. So let's go right to the notes. We had a little interruption in school today, so we're 15 minutes short in my 5th hour. All right. If I have time, I'll go back to that, but I really do want to stamp what I didn't stamp on Friday. Is everyone okay so far? Yeah, it was a false alarm. Somebody's elbow hit the blue button, one of our construction workers. All right. Okay. So, and then this is what I did with the other hour, and I'm still going to do it. Go to this third page, which is your bigger page. What does this mean? Where's your homework? Online again. Online. Draw this. We're going to draw a magic Ferris wheel. Look at that. Isn't that cool? And then here, that's not going to be as good, but not too bad. I want to center this a little bit better. We're going to do a magic Ferris wheel. I did this the other hour. Okay, the one time I do like this feature. So you have a choice. You can sit at seat A. You could sit at, and you know a Ferris wheel, how it works. There's an arm, right? There's an arm, and then the seats sit at the end of the arm, and then it rotates, right? And then you could sit at seat B, or you could sit at seat C. Interesting. What I want to demonstrate here is the difference between angular displacement, which is just this, and now that's the one time I did not want that to happen. Okay, angular displacement, I want that to look like that, and linear displacement over time. So let's say it takes, for one rotation to happen, let's say it takes 15 seconds. Let's just say that. Okay, so the angular displacement over time, which you're going to find out, is this letter W. Look at page 2 of your notes. Do you see that fancy little W? Page 2 is on that. Oh, right. I told you to go to the back to write this down. So this is theta, which is 2 pi, right? A full revolution. And then I just made up the time 15 seconds. Okay, so that's our angular velocity. Angular velocity. And I think this is more important to cover than maybe what's on the front sheet. Not besmirching it, but I always like my magic Ferris wheel to describe the difference between angular and linear velocity. Okay, so what's linear velocity? It is actually in the terms of v, but what's the velocity, linear velocity? I'm just going to do v after this. What's the linear velocity of seat A? What does that equal? I'm going to ask this in a different way. What distance does A travel over time? What distance does it travel when you're in seat A and you're doing this? What distance? 0. Now you could still get sick. I might still get sick because I don't like circular motion. As a matter of fact, when I go to Cedar Point, I don't go on anything that is circle, 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 circle. Blah! All right, that's what ends up happening. I'm glad to share that with you. So this is 0. Oh, and then I didn't give you any information. This is 0, let's say, feet per second. You travel no distance over time. You get it? But I still rotate one rotation over 15 seconds. Now let's say this one is like 10 feet from the center. Okay, so what is that? Well, the linear velocity of this is the arc length covered over time, and this is a radius, so that is 10 feet per second. Remember, times 2 is 2 pi r, so it's 2 pi r. That's what it is, right? 2 pi r, because we're doing a full rotation. So we did this all the way to this, which is a full rotation, a full circumference, right? And then that's divided by 15 seconds. Can someone type that in and find out what it is per second then? Oh, that's actually, no, it isn't. 2 times 30. Isn't 30 over 15 2? Okay, that's just a coincidence. What's 2 pi? 62.28 feet per second, right? Must have done different seconds last hour. Correct? Isn't 20? I'm a maroon. That's not 30. There's mistake number 1. No, wrong. Okay, it's 20 pi divided by 15. I made some other mistake. One mistake last hour. And of course, someone in that class, you made a mistake right away. They didn't catch it. What's 20 pi divided by 15? Now I'm sitting there waiting. Now I'm looking like a moron here. 4.19. Not very fast. 4.19 feet per second. We could change that into, you're going to find out it's a bunch of dimensional analysis today. And then let's say this last seat is, let's go crazy. You want to get nuts? Let's get nuts. Let's say that's 30 feet away. So then this linear velocity is 30, 2 pi r times 2 times pi over 15. And by the way, I want you to recognize something. I want you to recognize that this represents angular velocity. This represents the angular velocity. And notice how I get the linear velocity? I just multiply by the radius. You see that? That's going to be one of our formulas that I'm going to use. What does that end up becoming? What does that end up becoming? What does that end up becoming? I'm just going to keep asking. What does that end up becoming? 12.57 feet per second. Then we could turn that into miles per hour and they get a sense because we all drive in a car and we know what miles per hour are. And that's just dimensional analysis. So who would rather be on seat C? Raise your hand. Who's an adventurer? All right. So you have to understand this is just one rotation, but this is a longer distance over the same time. That means on the outer edge, you're traveling faster over that same time. I actually watched a YouTube video, and this is not at all probably related, but it kind of made sense about, you ever hear of time dilation? Do you ever hear the fact that if you travel faster, time slows down? Anyone ever hear that fact? Nobody? And if you approach the speed of light, and you travel at the speed of light, what time passes by? Anyone know? None. Isn't that crazy? All right, so it's crazy. In the time dilation, they were doing something about that. They had actually an astronaut. We don't have time for this, Mr. Samuels. I couldn't. Anyone? Care less. They had twin astronauts, and they sent the twin out to space and traveled out on the outer orbit. Same idea as, he's on Earth, but his twin is out there. And they proved that twin aged slower than his twin because they had an atomic clock on the thing as well. Isn't that crazy? Anyway, all right. So let's go back to our block and what we really need to know. There's your W. Okay, this is actually omega. That's good. So what is angular velocity? Angular position per unit of time. So this is some theta divided by some unit of time. It could be in minutes, in inches, minutes, seconds, hours. Could be any of those. All right, but we got to make sure that your angle is in radians, not degrees, not anything else, not rotation. So we're going to have to do some conversions. It's going to be 100% dimensional. Are you okay? You're rubbing your eyes already. All right, radians over time. All right, so read those three. And tell me who is ready to be placed as angular velocity by definition. And by the way, we got to get rid of these. Somehow the font changed with the line above it. There's no line above that W. It's just W. Okay, which of the above examples can be called W then legally by definition? A, B, or C, or none of the above, or one of the above? Name the letters. 3, 2, 1, go. A, I heard you. That just proves that you're reading. You're not a slug, a charlatan, a bum. All right, you actually read and you see that only can it be in radians per unit time. The other ones are not so much. Find the angular velocity above in radians per minutes. So here's letter A, that's in radians per what? So all I have to do is change that to radians per minute. So this is 2 pi radians per hour. And then here's your dimensional analysis. How many minutes are there in an hour? Where do I put, is it 1 over 60 or 60 over 1? What do I have to multiply by then? 3, 2, 1, go. And this kills me, anyone that thinks this is tough. Anyone that cannot do dimensional analysis, I'm going to have to call you a charlatan bum. Because all you have to do is write the fraction next to it that's equal to 1. And then to make sure that the word hours cancel. How is that hard? You have to be so fractionally challenged that you don't get that you need to go back to 6th grade. You're gone. All right? These are the kind of things that happen in this class. Like ripping off a Band-Aid. I have no patience for any of it. I got to teach someone new the Samuelis ways. I got to really add it up here and catch her up from first semester. You're a veteran. You can help her. She's been through this twice. Or 1.5 times, really. All right? Okay, calm down, Mr. S. All right. What's a DVD? I know that's going to happen in like 4 years. Someone's be like, what's a DVD? I've never heard of this thing. Is there an app for that? I don't get it. All right, a DVD, whatever that is, rotates in 108,000 degrees. Whoa. And it is per minute. Do I have to do any changes according to these directions in minutes? No, but I do have to change the degrees. So, whoa. 108,000 degrees per 1 minute. But I got to convert degrees to radians. What's the conversion? Is it pi over 180 or 180 over pi? 3, 2, 1, go. It's pi over, why is it pi over 180? So who cancels? Degrees. And now I can really treat this as dimensional analysis, and that's all you have to do. Now it would be in radians per minute because degrees are gone. You have to be so fractionally challenged to not understand this. I'm sorry. It's not this that we're doing right. We're doing actually dimensional analysis with basics of it. And understand that this fraction, both of these fractions equal 1. That's why this doesn't change anything, because of labels and things that are equal. And then revolutions, 70 revs per 1 minute. Do I have to do anything about minutes? No. How many radians are there in a revolution? I told you, he told me, did you get arrested over the weekend at Walmart's parking lot? My math teacher told me to come in the parking lot and do a bunch of 2 pi's. Okay, so how many radians are there in a parking lot? In a rotation, sorry. 2 pi. Where does it go? Top or bottom? Top or bottom? Top, because it's 2 pi rads per 1 revolution. Got it? And then you can beep, boop, press all the buttons and press enter. You okay? All right. All right, now, it took me a minute for why do I have 3 different V's here? What's V stand for? Velocity. As soon as you see V, velocity, that means you're in concrete things that make sense, like distances, like this thing. This is a yardstick. So 1 yard per minute, that means you traveled this far in 1 minute. Very simple. It's not a rotational thing. It's this, but then it'd be arced. I don't want to break this. So it's ooh, I wish this is more bendy. All right, but it's an arc that you're traveling along. Circular movement. What are the planets? What do they travel in? What kind of rotation? It's not circular. You stopped. What is it? It starts with an E. It's almost circular. It's elliptical, though. All right? Okay, so you know what I didn't get to do because of time? What's S? What was that letter for? Friday. What was that letter for? Arc length. Okay, and S you found on Friday was R theta, as long as theta was in radians, right? And we do have it right here. So, what's velocity? It literally is arc length, which is S, divided by time. The arc length traveled over time. That's why we have that one. Okay, we could do that, but I think a better formula is, what is arc length? Which is R theta, which I just put up there, divided by time. But then what new letter did you just learn? You just learned a new letter. What is that? That's W, which is angular velocity, which we need to make one more change there. We got another, like that font got weird. Okay, so that is now possibly replacing that with W, you'd end up with this. And then this is the one I'm going to use the most. All 3 of these formulas are the same. The last 2 are the most useful, though, because they have all the components. The middle one's pretty good, too. But the way the questions are constructed, they ask for what's the angular speed, then what's the linear speed. So then I'm just going to multiply by R, right? Okay, and then it'll all make sense. Boy, a lot of yawners here. Mondays are just rough. Monday, la, la, la. Okay, shut up. Why is this linear velocity? It's in terms of inches and feet per time. A discrete a distance that makes sense to me. Looks so nice outside, but man, it's just so bitter. Oh, I walked into school today and I walked this long way outside. Oh, my face was frozen, my nose was frozen. Really miserable. Like I was getting punched in the face with wind as I was walking in. Just like okay. Neighborhood Carnival has a Ferris wheel, good for that, with a radius of 30 feet. Hey, that was my radius, the outside seat. Measure that the time it takes. You can look at this. You can see, like, I can see someone on the Ferris wheel and see there they are, and then 70 seconds, there they are again. I could actually do this. I can sit there with my timer. I won't go there anymore because Chicago's a cesspool. But Navy Pier, does anyone ever been on Navy Pier's thing? The Ferris wheel, the new one or the old one? The new one. I didn't go on the new one. That's bigger. Yeah, but it never stops, does it? No, it doesn't.
No, it doesn't.
No, it doesn't, because you got to get off and get on, and if you don't get on and you're hanging on, you're gonna be hanging by your belt as they go around. They ain't stopping at all. All right. So no, it never stops, but it goes very slow. That's why. So people can get on and get off. Right. What is the linear speed in feet per second of the Ferris wheel? Look at this. What is the linear speed? This is a little out of order. What is the angular speed in radians per second? Guess what? I'm going to do that first. I'm going to put that right here. What time is it? 39. Okay, so what is the angular speed? That's W. And that equals theta. Well, that's easy. What's a full rotation? 2 pi, and it's in radians per second. How many seconds did this take to do? 70. So there's our angular speed. It is, you could reduce this or you can make it a decimal. I'll just leave it like this right now. You feel free to do what you want. You want to make it a decimal, go for it. It's pi over 35 radians per second. That's the answer for angular speed. Now, I don't know. You already figured out the formulas here. Why would we not use them appropriately? I'm just going to use this one. Okay. How do I get the actual velocity in feet per second? Let me get my highlighter. I take and multiply that by r, and I hope you understand why. But I'll go back to the original, or I'll like write it in terms of the second formula. What's linear velocity, which we use with a v? It is the arc length, which is 2 pi r. Here's r, so it's r 2 pi, right? 2 pi r, a full revolution in 70 seconds. But that's why I was just going to take and multiply 30 by W, because that's what W is already. And then that's what's so weird. When you take radians and you multiply them by feet, oh, isn't it 6/7 pi, right? Reduced. Whenever radians is multiplied by a concrete, what am I trying to label? But I'm trying to say, what would feet, miles, what's another word for that? A distance? Some measurement? Thank you. Whenever it's multiplied by a measurement, it turns into that measurement. Why? Because a radian, remember, is this. Here's a circle. Come on, do it. Yeah. Remember, if this was like 2 inches and this was 2 inches, what is this as a radian measure? What is that as a radian measure, everyone? 1 radian. 2 inches over 2 inches, the inches cancel. What's left over? The magical radian. So what happens when you hit a radian with inches? It turns into what? It starts with an I and ends with inches. What are we doing here? Okay? When I take a radian and multiply it by a mile, what does it become? It starts with an M and ends with aisle. Mile! Ah! We're just looking at me like I'm some sort of freak, which they're right, but you don't have to look like that. All right. Circular blade on a saw has a diameter. Remember, I screwed this up. I admitted it. I screwed up 4th hour, and I didn't read diameter. So what's the radius? Let's get it over with. No time. Everyone's just looking at me. Is that right? 3.25, 6.5, 3 point what? 7.5. I never was good at math. Rotates at 20, it's always my hardest subject, 2,400 revolutions per minute. 2,400 revolutions. So find the angular speed in radians per second. Okay, so W equals, so I don't need this yet. This is for this. Having the radius has nothing to do with angular speed. So it's 2,400 RPMs, revolutions per 1 minute. What do I have to put this in? Starts with an R, radians. So all I have to do is turn this into radians. Wrong. How do I turn minutes to seconds? Let's do that. So is it 1 over 60 or 60 over 1? Why is it 1 over 60? You're a charlatan if you don't get this. You don't write your work. Try to write as little as possible, and this is why you get wrong answers. All right, it's probably not you, but let's not talk about the other classes. Okay, and then times, how many radians are there in a revolution? Where does it go? Is it 2 pi over 1 or 1 over 2 pi? 2 pi over 1. Again, you're half listening if you don't get this. If you ask me, I don't get where you're getting these fractions from. Guys, fractions. This is basic skills. The word revolutions cancels. The word radians is left over. Lo and behold, I have radians over seconds. It's the simplest thing in the world to do. Please help your science teacher. All right, and then this is in feet per second. Let's just do this. V equals RW. This is already in radians per second. So it's 3.75 times the previous question, right? Can I move on because we're short on time? Right? Okay, and that's how I find linear velocity. I just multiply by the radius because of how these formulas work. All right, and then get the decimals. Please be careful on how I think in the other hour, we only have 10 minutes. Yeah. Is this the last one? Okay, we'll do it real quick. All right, a second hand of a clock is 6 inches long. Yeah, it's probably something on the wall then. 6 inches, about that big. All right, what is an angular speed of the second hand in radians per second? What is going on here? That stopped happening, I thought. Angular speed of the second hand in radians per second. So we do 2 pi radians. Trying to think of the right letter. We do 2 pi radians in 60 seconds. So this would be pi over, I feel like it hit 15, I don't know. Sorry. Rads per second. I do understand when I write this like this, top and bottom. And then you can go ahead and get a decimal for this. What is the linear speed of the tip of the second hand in inches per second? It's just as simple as this. It is 6 times pi over 30. All right, and then that turns into, isn't that pi over 5? Inches per second. It's the magic of radians. Radians come from concrete measurements. Thank you for that word. So therefore, they turn into those measurements when they're multiplied by those measurements. It's true. It's the whole thing why I said this up here. When I multiply radians by inches, how does it turn into inches? Because radians came from inches, feet, miles, so on and so forth, through this idea of what a radian is. Last but not least, I like this one. It's a little different. So I do have to work with my formulas a little bit. A race car is driven around a circular track 180 miles per hour. You do know that's about a reasonable speed for race cars. And then also my speed when I'm going home from this place. I'm just kidding. It's a joke. I love it here. All right. So the velocity is 180 miles per hour, 1 hour. And then I know what's going to happen here. If the diameter is a half a mile, let's not trick ourselves then. What's the radius? What's the radius? A fourth of a mile. What is the angular speed of the car? And then I actually went further, like how many rotations happen an hour. But let's do radians first. Well, we also have to know our other formula. Isn't it r theta, which is arc length over time, right? Now I separated the r out of there, right? Because what I need is this. I need just that. So what do I have to do to this to get theta over time by itself? I have to, divide by r. Or I could put this in. Okay, r is 1/4 of, you could kind of put it up there, but you could keep it up here too as well. 1/4 over up here is the same thing as 1 theta over 4t. Hope you know that. Okay, it's still multiply both sides by 4. So the velocity is, no, wrong. The W is, because I got rid of the radius out of there. My bad, dogs. And then you're going to find out 4 times 180. Oh, man, someone's really yawning a lot in here. We're all going to faint here shortly. Oxygen hog, radians per hour. Anyone ever go to one of these races? That's fun. Those are vroom, 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 vroom. Because then what we did, this is the answer, but then I said, you know what else would make most sense is rotations. How many times would they go around the track? You know, that would be a fun one to answer. How do I find revolutions? How many revolutions are there in a radian? Or how many radians in a revolution? So I would have to divide by 2 pi, because that's 1 revolution, to find out how many revolutions there are. So take 720 divided by 2 pi just for fun to see how many revolutions happen in an hour. How many times do we see these cars go around the track? And then I'll end on that one. It should be 720 divided by 6.28. If you didn't get like 100, what's the answer? 114, about 114 revolutions per hour, which is reasonable. That is true. That's what these cars do. They're pretty fast. But the answer is 720 radians per hour. I was just playing around with it. Where's your homework at? Online. Yeah, I have 5 minutes to stamp, and I'm going to do it real fast. End the movie.